It is a recreation of a very famous experiment that proves to us that we live on a rotating planet. So, it's a very simple experiment that uses this giant pendulum. Raise your hand if you have ever seen a pendulum before today. A couple people, right? Probably not this big. Right? Somebody's desk and just looks like, something like that right away from me, right? So, a pendulum is a very simple machine that is only good at one thing. Can anyone tell me the one thing a pendulum is good at? Shout it out. Dare to be wrong. Moving and what? And tell me more. In a straight line, right? Oscillating between the same 2 points on the same plane forever, right? As long as it meets 2 criteria. It has to have constant energy, and it can't be acted upon by an outside force. So Newton's third law of motion tells us that an object in motion will remain in motion unless acted upon by an outside force, right? So as long as a pendulum has power and nobody touches it, please don't touch it, right? It can only swing in one direction. It literally can't do anything else, right? Because it doesn't know how. It doesn't have a brain or a motor or an opinion, right? So this is true for every pendulum in the universe because physics works the same way everywhere in the universe. So it's true for this giant pendulum. So we have, what is it, right? So we have this giant brass pendulum ball. It's about 240 pounds. It's connected to this steel wire. This steel wire is attached to the building. It's fixed to the building with a ball joint. So think about how your arm connects to your shoulder or how your leg connects to your hip, so it can move around in a bunch of different directions. Remember that ball joint. We'll come back to it later. And then around the wire, fixed to the building, this does not move, is an electromagnetic ring. So that provides the power. You turn on the electromagnets, right? And it starts to repel the wire back and forth inside of the ring. So because it's being repelled, right, the wire never touches the inside of that ring. Okay? And now we're going to do some observational science together. Is everybody ready? You're like, oh, I didn't sign up for school, but it's happening, so it's too late, right? So, simple yes or no question. Simple yes or no question. As we observe the pendulum, does the pendulum ball touch the walls of the pit? No, it does not, right? We're all seeing that together in real time, right? So, again, going back to how a pendulum works. As long as it has power, constant power, and it's not affected by an outside force, it's just going to keep swinging back and forth. So as long as the power doesn't go out, and again, because we know the pendulum doesn't touch the wall, as long as none of us touch the pendulum, please don't touch the pendulum, this pendulum is only capable, like every pendulum in the universe, of doing one thing, swinging back and forth in the direction that we're watching it right now, yeah? So, again, simple yes or no question. Do we have observable evidence of motion in this direction? We do, because we can see the pendulum move. Great. Very good, great, very good class. So, now we have this tray of pegs at the bottom of the pit. And we can see that some of the pegs have fallen, some are still standing up. Why did those pegs fall? Every 7 to 10 minutes, there's a little extension, a little pit on the bottom of the pendulum, knocks down a peg. So we're going to do some deduction together, right? So, I assume none of us were here when the first peg fell. Maybe you were. Congratulations, right? So even if you were not here, including myself, I wasn't here when the first peg fell. Does anyone think you can guess which peg fell first? Which peg do you think fell first? The one on the farthest end here, right? Cool. Do you think you can guess which peg will fall next? Which peg will fall next? The one that just fell, right? Yeah. Do you think, again, taking it to its logical conclusion, do you think you can guess which peg will fall last? Which peg will fall last? The one on the farthest end, right? So based on that, even if we, without having to stand here for 2.5, 3 hours, do we can we logically deduce that there is motion going in the direction that the pegs are falling, right? Because we see the pegs fall, there is a sequence, right, that is not random. So based on the direction the pegs are falling, now we have evidence of movement in a second direction, right? So now we have observable evidence of motion in two directions, right? The pendulum swinging this way and the pegs falling that way. Yes? Well, what do we know about pendulums? Can a pendulum move in two different directions on its own? We know that it can't. Right? We just talked about it. So here's the experiment, right? So if we have evidence of observable evidence of motion in two different directions, and we know that that pendulum can only move in one of those directions, in order for the pegs to fall, something else has to be moving. Because the pendulum can't make it happen on its own. So what's the other thing that's moving to cause the pegs to fall? The earth, whatever the tray is sitting on top of, right? So, which happens to be a rotating plane. So what we are observing is not the pendulum moving towards the pegs. It is the tray on top of the earth rotating into the path of the pendulum. Right? Now, you're going to stand here for hours, your eyes are going to tell you the pendulum is moving around the pit. Right? Because your eyes are stuck inside your skull. Your skull is attached to your body, and your body is trapped by the Earth's gravity. So, because we are on the Earth as it's rotating, we're moving with it at the same time, and you cannot perceive with your five senses the rotation of the Earth. It's too big, you're too small, right? Sorry, it's just true, right? So, everything except that pendulum is moving together around the pendulum. Now, remember that ball joint I mentioned that attaches the wire to the ceiling? So that ball joint, now that we know what's moving and what's not, or how things are moving rather, because everything's moving, the ball joint is not there to allow the pendulum to rotate around the pit, because we know that's not actually happening, right? It is there to allow the building to rotate around the pendulum, because that's what's moving, along with all of us, right? That's what's rotating, right? The pendulum is moving, but it's just moving in a straight line. So those are the mechanics. That's how it works. And then we have all these numbers around the pit. They're super fancy, right? We did it 3 times. So these are all 1 hour increments. So it's a total of 0 to 41. So it's a total of 42 hours. So it's not a clock, because that's too many hours, right? That 42 hours is the amount of time it takes at our local latitude. So just a reminder, latitudes, look at a globe, it's an imaginary line, runs east-west. From the equator to the poles, runs east-west around the globe. At our local latitude in Los Angeles of about 34 degrees, it takes about 42 hours for the Earth to make a full rotation around this pendulum. Okay? So if you build your experiment at a different latitude, your numbers will change. Right? So if you're at the North Pole or the South Pole, imagine there's a big stick, right, running right through the center of the Earth. That's our axis of rotation. So that stick is creating all the rotation for the entire planet, right? It's all being generated right through the center. So if I'm at the top or the bottom of that stick, I'm spinning the fastest, right? So it only takes 24 hours at the North or South Pole. So let's say this is the North Pole, this is our axis of rotation, right? So as I start to change my latitude, getting closer to the equator, right, I increase my distance and my angle from the axis of rotation, right? So again, my experiment starts to take longer. So it's 24 hours at the North Pole, right? About 42 hours at Los Angeles, wherever Los Angeles is, right? And then you get to the equator, and the experiment doesn't work anymore. So the Earth is still rotating, right? The pendulum still swings, but because the pendulum is now swinging perpendicular to the rotation of the Earth, so it's a relationship like this, basically. I guess like this. Because of the physical relationship between the swing and the rotation, there's no perceived rotation of the pendulum as you watch it, right? You can also think of it takes an infinite amount of time to observe rotation of the pendulum. Another way to think about it, right? Because it's weird, right? Because a planet rotates wherever you are on it, right? That's just true. That's how planets work, right? So if we think of it not in terms of, the experiment doesn't measure rotation, because again, the planet rotates wherever you are, it measures twist. So the twist that causes the rotation only gets generated through the center of the planet from north to south, right? So if I were able to like break off my finger, right, gross, and then place it on the North Pole, my finger, it's not attached to anything. As the Earth spins, it's just going to spin all the way around, right? So it's twisting all the way around at the North or South Pole. As it starts to travel across the surface of the Earth, changing latitude, it's still rotating, right, as the Earth is rotating, but it's twisting less, because all the twist is happening this way, right? So it's traveling, so it's twisting less and less. When I get to the equator, there's no more twist at the equator, right? Because a planet can't twist in two directions at the same time, right? It can only twist on one plane or the other, right? So all the twist is here, north-south, not across the middle or east poles. So that's just another, I find it helpful. It's another way to visualize why the experiment doesn't work at the equator, even though if you're on the equator, I promise you're still rotating along with the planet. You're just kind of twisting with the axis of rotation. So another peg fell, so I've been talking too long. So that was our Foucault pendulum. Thank you for listening. If you have any other questions, please let us know. And enjoy the rest of your day here at the observatory. Okay.